Well, I am going to try to make a video of how to do one or maybe some of the more challenging problems on Lab 4 for our Physics 214 lab. This one is about ammeters and voltmeters, and we're going to be putting very sensitive type of ammeter called a galvanometer into our particular circuits, and we're going to determine a way. There are ways that we can use we can adjust the amount of current going through these to do one of two things. We can either turn this galvanometer into a voltmeter, or we can, with a different arrangement of resistance added to it, will give us the ability to turn it into an ammeter. So our first question, again, we're going to whiteboard this, which I don't usually do, but maybe I should give it a shot. So here's from a previous semester, kind of the gist of it from the lab manual, and I hope that the one in your lab manual looks like this. Maybe it's not all written on in red ink like mine is, but this is the gist of the problem. They're wanting to know how we can take a galvanometer with a known internal resistance of 50.0 ohms of resistance. We're going to have to, and this galvanometer is pretty sensitive to a current going through it. In fact, it's known that this galvanometer will give you a full-scale deflection one way or the other, positive or negative, because these things are usually centered at zero, and then positive direction of current will deflect it. And again, we're going to use these for direct current measurement. So one direction of current is going to give you a positive value. If the wires are switched around and our current's flowing the other way, then we're going to get a negative deflection. So I'm going to just treat everything hopefully on the positive side of this. And so to get a full-scale deflection, or with actually a very small amount of current, we're going to get a full-scale deflection. And that happens to be 1.25 times 10 to the negative third amps, or what would be, in terms of milliamps, would be 1.25 milliamps. But we're going to work with it in amps so we can get our correct SI units. And the question is asking, so if we look up here, I've written that we've got the galvanometer, the R sub G with 50.0 ohms. We need to know what kind of, in order to do this, here's one of the key things. When we put, I don't know if I can do this very well, if we put a resistor in series with the galvanometer, what we're doing essentially is now we're making that into a voltmeter, because this is saying if we want to take this and make it a voltmeter that will be able to read 50 volts, I'm sorry, I think it's 5 volts, why did I say 50? 5 volts of electrical potential, we need to know what kind of resistor to add to that in series. So we have a galvanometer, a resistance that we're adding to this in series, that's going to make this into a voltmeter. So then now we could use that, that arrangement to measure electrical potential difference, or voltage, and we'd be able to read whatever this voltage, there we go, whatever this voltage source is. And this is new for me, so bear with me. It's probably going to be a little bit awkward, but I'm going to muddle through it here best I can. So the question's addressing what does that series resistor, or R sub S, what value, what resistance does that need to have to put in series with the galvanometer to get a 5 volt full scale deflection? So we're essentially saying we want to change this into a 5 volt or a voltmeter that has a range of 5 volts of electrical potential. There. Basic application of resistor properties. Again, you did capacitance last week, and had probably already done some things with resistance in different combinations, series and parallel. Unlike capacitors, it's just the opposite in a sense. Resistance in series is just the two resistances added together. So if we want to know R total, or the effective resistance of the circuit, or the combination of components in the circuit, we just add them together. So R total is what we got to get first. We need to know what's the total resistance going through this in order to make it able to read 5 volts of electrical potential. Then we know some of these quantities. We know one in particular. We know the internal resistance of the galvanometer, R sub G. So I've checked that one off. Our unknown is R sub S, kind of our final unknown. At this point, we don't know R total, so I put a little star by it. But to get R total, we just apply Ohm's law. R equals V over I. And we know the voltage potential we want to be able to measure, which is 5.0 volts. We know that 1.25, and that should be, oops, I made a mistake, that should be times 10, let's see if I'm putting this in the right place, times 10 to the minus 3 amps. So again, we could have used 1.25 milliamps, but to get the right units of ohms, we need to have it in amps. So it's 1.25 times 10 to the minus 3 amps of current. 5 divided by that value, the current of 1.25 milliamps, or 1.25 times 10 to the minus third, it's going to give us 4,000 ohms, or 4 kiloohms. We sometimes might see that written as 4 K and then ohm. But I left this out to 1 decimal place of precision so that we're not hindering ourselves. If I just wrote 4,000, then we only have 1 sig fig. So we want this to have a precision comparable to what we have up here. We know that this galvanometer has an internal resistance measured out to 1 decimal place of precision, 50.0, 3 sig figs. We know our current value in 3 significant figures. Our voltage, our electrical potential, 3 sig figs. So we're going to try and keep this so we can end up with 3 sig figs in our answer. So here's what we do. We have our basic formula for series resistance, and just R1 plus R2. In this case, it's going to be R... where did I go? Oh, yeah, I guess I'm going back to this one. So it's just R1 plus R2, or our total is what we get when we know our internal resistance that's given. We calculate what the total is. So we just rearrange that. So now it's going to look like R sub S. Our series resistance is going to be the total minus the resistance of the galvanometer. It's 50 ohms of internal resistance. So that would just be 4,000.0 ohms minus 50 ohms will give us, and again I used 50.0, and we get 3,950 ohms. And it works out real nice because it's at the right number of significant figures. So that's problem 1. That's why these problems are crucial to this experiment. They're time consuming to try and go over all of these in lectures, so be working on them, and I'll post some more videos and things like that to hopefully help you out.